Hey everybody, welcome to chapter 3 where we are going to start looking at chemical bonds. So we started chapter 1 looking at matter and stuff and how everything is kind of categorized. And then we came down to elements, which are like the purest form of matter, and we ended up with the periodic table. And we looked at all the chemical properties of all these different elements and whatnot. And now we're going to take those ideas that we had with like matter and all the different categories and everything we learned about the elements from the periodic table, and we are going to see how those elements interact together and what they do to like stick together and like make stuff. So how do we go from atoms to compounds and stuff? How do we go from elements to like everything else that you see in the entire world? And to look at that, like how we go from just elements, like one atom at a time, to, everything, we need to look at this. Chemical bonding. Boop, know that right there. So chemical bonding, this is basically like, it's what holds atoms together. I mean, that's like the definition of what chemical bonds are, but we're going to dig in a little bit more than that, right? Because we're going to look and see like what, how, and why, okay? So chapter 3, chemical bonding. First off, how do these things even happen? Well, it starts out by these negatively charged electrons of one atom are attracted to the positively charged protons of another atom, right? Electrons and protons, they're not like alive. They're like, once they're involved in like an element, they don't know that they belong to that element, right? They're just a positively charged thing and a negatively charged thing. So if you get two atoms kind of close together, we'll call that an electron cloud. We'll call this another electron cloud. Like these electrons are going to be attracted to those protons, and these protons are going to be attracted to these electrons. Like, it's just kind of how it is, because they're both oppositely charged. And when those oppositely charged particles start pulling on each other, I mean, not always, but sometimes some really crazy magical things happen. Obviously not all the time, because look, those atoms are like about as close as they can get now. See, pen and mug. But there's no chemical reaction, so why? Man, why? Why is it if I can take a pen and smack it up against my mug, there is no chemical reaction, but other things, man, there's like quite a chemical reaction, like you saw when I just put sodium or calcium in water. Man, was there a reaction. So that's the driving force right there. Like that's what drives. This is what drives chemical bonds. And a little positive being attracted to a little bit of negative. Bam, some magic happens. So what do they do? What do they even do? Well, they hold atoms together. That's okay. I figured you might be able to like put that together, given they're called chemical bonds. Right? So they bond atoms together, right? And when this happens, like the way that chemical bonds hold the elements together is by shifting electrons. They just shuffle them around. And really, we are only going to have two categories that we're going to dive into really deeply. They are either going to be shared or they are going to be transferred. Now, shared literally means shared. So there's two atoms, they come together and they start sharing electrons together. Or they are transferred. In other words, like you have atom 1, here's atom 2, electron leaves and enters this one, no longer there. This one over here gobbles them up, this one over here loses them completely. So the names for that are ionic. This is where electrons are transferred, and we call it an ionic bond because I'm sure you remember when you lose electrons, the atom becomes positive, right? So that's like when we had sodium turns into sodium plus 1, and chlorine turns into chlorine minus 1. So the sodium atom lost an electron and became a sodium ion. The chlorine atom gained an electron, became a chlorine ion. And now these two things are going to stick together because they're ions. That's why it's an ionic bond, because they're ions and they stick together. You got it? Now this next one, covalent. Let's look at this for a minute here. This is like a thing. Like to cooperate is to cooperate is like working together. To cohabitate means to like to live, like, or to share a dwelling, and to co means together. So this prefix here means like together or shared, right? That's what the co part means. And the valent, man, if we're talking about electrons, what do you think the suffix valent might mean? I'll give you a minute to really like dig into that. Yeah, valence electrons, right? So a covalent, like it's right there in the name, it means sharing valence electrons. And that's exactly what it is. This is when electrons are shared. We call it covalent. Got it? So those are our two main types of chemical bonds that we're going to be looking at in this chapter. Are there more? Absolutely there's more. Are we going to dig into them? Eventually, but not too terribly much. And this is the other thing they do. So here's one thing. One thing is that chemical bonds hold atoms together, and the other thing they do is they store energy, right? Like I get super duper hungry, I eat me a Snickers bar. Why? Because they're so good. Lots of energy, right? I mean that's what's inside a bond. A bond, yeah. It contains stored energy, but we're gonna dig into that a little bit more because a lot of people think that you get energy out of from breaking those bonds. So they see something like this with like the crunchy cookie and the creamy nougat and the delicious caramel peanut topping. Oh my gosh, I am really hungry right now. Why do I do this to myself? And they think that, or they're taught that when you eat something like glucose or food, that you break the bonds and get energy out of it. But we are going to learn what actually happens, like how you actually get energy out of a bond. But it does, like chemical bonds can act as like little chemical batteries where they have like stored chemical energy. And the best example of that is food, because we need that energy that is stored in food. It's chemical energy. So here's the thing. When we talked about it, I'm going to do a lot of zipping up and down here. So how do chemical bonds form, right? They like shuffle electrons, right? They're either shared or they're transferred. And it's not totally random. Like there are like laws of nature that govern like which electron goes where, why, how, all that kind of good stuff. And the main rule that we are going to be looking at, like the main like law of nature that we're going to look at, is this thing called the octet rule. So electrons are shuffled, like shared or transferred, around, and yeah, no judging. They're gonna be shuffled around to satisfy what we call the octet rule. So this octet, an octet means 8, like ocho, an octagon, right? So just like the noble gases, 8. Every atom wants to have 8 valence electrons. So the atoms will gain, they will lose, or they will share electrons to have 8 valence electrons. Or if they can't have 8 valence electrons, they'll have an 8 electron outer shell. This is the more important idea that I want you to have. They have to show 8 out to the world. So whatever shell it is that's on the outside, that outer shell, it's got to have 8. So some atoms are going to gain electrons, and then their valence shell is going to be like full of 8, locked down, super crazy atomic iron, solid stability, awesomeness, right? However, some like sodium and calcium, the stuff that like I dumped into water, and they actually lose electrons. And when that happens, like we're gonna do this again, but like sodium has an electron configuration of 281, right? And so what sodium does is it gets rid of that outer valence shell, and look, there's that magical super satisfying 8. You got it? So that's what I mean by the outer shell. The valence shell is gone. Like sodium lost all of its valence electrons. Valence electrons gone. But the one that it shows out to the world is 8, and that's super duper crazy solid. I hope that makes sense, and if it doesn't, don't worry, because we're going to be like going over this a lot. And when they have 8, right? When they have 8 valence electrons, they have a complete outer shell, stable, solid, will not react. Does that make sense? The whys, man, if you want to know why 8 valence electrons are so stable, join me in Chem 101, and if that doesn't satisfy you, you have to go into particle physics. It's kind of like, all these subjects that we have, like chemistry and physics and math and like environment and like all that stuff. they all kind of like go together, and so there's like fuzzy boundaries. So you want to know why octet rule? That's really like particle physics. It's like chemistry and physics together, you know? Just like, yeah. Anyway, so, here's a thing, man. Here's the thing. Whenever energy is released by the formation of bonds, the products are more stable. And this is going to get into something that's a little bit trippy that I want to have. And it's going to look like this. Here's a single iodine atom. Here's another iodine atom. This arrow means that there's been a chemical reaction, and now they make I2, right? The diatomic, because that's how it really wants to do. And it will release energy. Usually chemical reactions release energy in the form of heat. Sometimes it's light, you know. But that's how we know that energy is being given off. There's light or there's heat, and we can measure it, right? So in this particular chemical reaction, because energy is over here on the right, because energy is here, it means that energy is leaving. So that means that there was more here in these two things, and there's less energy in this product. And if there's less energy, that means it is stable. You got it? That means it is stable. So anytime energy is released, that means that your products are more stable. There is less, in other words, there is less stored energy in this than there is here. And you can kind of think of this analogy as like a wound up rubber band. You guys ever do that thing where like you wind up a rubber, there's like this little like toy like airplanes that are made out of like balsa wood or something, and you spin the propeller, and you let it go, and you never go straight and crashes or something, but they're fun. So that spun up rubber band has stored energy in it, right? And if you let it go and it goes, that rubber band, when everything is all done, has less energy. It's more stable. And where did all the energy go? Well, it went into moving the plane through the air and whatnot. So that's kind of what this is like. When a chemical reaction gives off energy, the product is more stable. It has given up energy. You guys dig that? Oh. What? No, we should just keep going. This is insane. This is only like, I feel like I haven't even gotten riled up and yelled at you yet. This is insane. Why should we? But I guess we will. We'll end right here, and the worksheet that basically covers all this wonderful, wonderful stuff is called How Bonds Form. And for this, we're going to go back to that the board diagram of the atom with like the different layers and shells and the electrons in each one. We can see what happens and stuff. Man, it's going to be amazing. Don't act like you're not happy about it. All right, guys. So thank you for paying attention. Thank you for writing this out with your hands on a piece of paper. It's backed by science, not just because I'm a sadistic, evil chemistry teacher, but because I insist that you learn. Yeah, thanks for being awesome. You guys have a great day.